SwayamPrabha. Digital India. Educated India.
Let's take an example of the structure which is shown in the PPT. Is the 3-element structure, and each one of them is a truss element. And then there are 3 members, 1, 2, 3 in circles. And then they are also connected at nodes 1, 2, and 3 as shown. And the dimensions are given. It's a 2 meter by 2 meter. And then the loads are applied at 100 kilonewtons, 200 kilonewtons, as well as there are some boundary conditions at node 3 and 2, which are hinged or pin connected. So this is the structure. And then we would like to formulate the equilibrium equation for the global degrees of freedom. In the sense that here, the degrees of freedom or the primary degrees of freedom are the displacements at node 1, which we call as u1, v1, and at node 2, u2, v2, and at node 3, u3, v3 in the direction of x and y axis. And then, of course, the derived degrees of freedom are the nodal forces at 1, F1x, F1y, and at node 2, F2x, F2y, F3x, F3y at node 3. So these are the 6 degrees of freedom for the system, whereas each node is an equilibrium equation in 4 degrees of freedom. And in the last class, we talked about the 4x4 stiffness matrix for an element which is at a general orientation alpha. So changing the alpha here, we can get the equilibrium equations or the stiffness equation for each element. For example, the element 1 is vertical, and then we can consider the node 2 and 3 are aligned at an angle of 90 degrees from x-axis, while the element 2 is aligned at 180 degrees starting from 1 to 2, or if you consider it as 2 to 1, then it has the angle is 0. So similarly, the element 3, which is in the orientation of along 1, 3, is at an angle of 135 degrees. So this particular data, you can see it, which we call it as connectivity data, which is represented here element by element 1, 2, 3. Element 1 is connected to 2 to 3, so which you can see here. Element 1 is from 2 to 3, which is at an angle of 90 degrees, as I was telling. And then there are some area, and then it's made of some material here. Element 1 is made of aluminum, and element 2 and 3 are made of steel, which have Young's modulus 200 GPa, as well as the cross-sectional area is also needed. And of course, the length of the element is needed as L. So we know that, so coming by element, so element 1 here is at an angle of 90 degrees. If you recall, the K of the element is a 4x4 matrix. And then it is, if you just look back, so it is AE by L, which is common to all the numbers. And then the various expressions for each element is cos square alpha at the top, and the row continues as cos alpha sin alpha, minus cos square alpha, and minus cos alpha sin alpha. Like this, all the 4x4 expressions are there. If you look into that, then this is the 4x4 matrix, which you can, this is the 4x4 matrix. So similarly, element 2, as I said, that it can be considered as alpha is equal to 0, And like here, element 2, if you go back, element 2 is along the direction 2 to 1. So here it's also very important that node 2 is considered to be ith node, the first node, and node 1 here is considered to be jth node. As such, then the direction of element 2, 1 is at an angle of 0 degrees from x-axis. So like this, so element 2 is at 0 degrees, and then the stiffness matrix comes out to be like this: 2 into 10 power 8, 0, minus 2 into 10 power 8, 0. And the second row is completely 0. And the third row is minus 2 into 10 power 8, 0, 2 into 10 power 8, 0. And the fourth row is completely 0. So similarly, the continuing to the third element, you can see the third element is along the direction 1, 2, 3, and it is at an angle of 135 degrees, right? So the nodes are 1 and 3. Okay, so this is element 3, well, is fully populated at alpha is equal to 135 degrees, starting from 1.7678, 10 power 8, and so on. So essentially, it seems to be the same value, because either it is cos square alpha, sin square alpha. When alpha is equal to 45 degrees, they are all same, either plus or minus, right? So that's why you have 1.7678 plus or minus. So these are 3 elements, and then these have to be assembled. So as we were saying, so yesterday we saw it in an elaborate manner. So looking at 3 by 3, so yesterday, if you recall, I'll just recall what was the thing yesterday we have done. We had, this was one day example which we talked about. One, 2, 3. So element 1, if you recall, so it has is a 2 by 2 matrix, and element 2 also is a 2 by 2 matrix. And then this connects the degrees of freedom u1 and u2, that's the displacement, and this is related to u2 and u3. So we have here k, and then these are the 4 numbers in the stiffness matrix, and then this we want to assemble in the, so when you assemble it in the, yesterday we have seen the equations in an elaborate manner, but however, we talk about a shortcut procedure, just the same equations. So here we have u1, u2, u3, and these 4 numbers here, for example here, so these elemental stiffness matrix will go to these places, and this is 0, of course. So this is 1 and 2, and this is 3, and then this is 1, 2, 3. So element 1 goes to here because it has 1, 2, and 1, 2 of global degrees of freedom, while the second element goes to 2, 2, 3. So that means that it goes to these 4. This is element 2, and this is element 1 here. So, but however, you should also observe here that this 2 by 2 here in the global degrees of freedom is contributed from the element 1 as well as element 2. So that means that here this goes to 2 by 2, and this also goes to 2 by 2. So that means that there is a addition of these things. So this is element 1, this is element 2, right? So this is what you have to remember of assembly. So like that. So now in the present example of the truss example, so you have, which is in 2D, and then there are 3 nodes and 6 degrees of freedom. So if you look at that, then so the element 1, for example, has nodes 2 and 3, and it's a 4 by 4 matrix. So that means that in 2, so you have U2, V2, and U3, V3. So this is element 1, right? And 2 to 3. So this is all the 4 by 4, right? And similarly, element 2 has like this. So it is calculated between the nodes 2 and 1. So that means that this is U2, V2, and U1, V1. And so similarly, element 3, so it goes to 1 and 2, right? So it goes to 1 and 3, I'm sorry. So it goes to U1, V1. So if these are the 3 elements which are supposed to take care of these degrees of freedom here, right? There's the element 1 and 2 and 3 here. So globally also you have to see here that you have U1, V1, U2, V2. So that means that like this. So if you look at, this is again 1, 2, 3, 4, 5, and 6. So you have to see here. So here, this is 2 and 3, right? So these are, so 3, 6 degrees of freedom. Either, if you want, either call it as 1, 2, 3, 4, 5, 6, or maybe corresponding to U1, V1. You can also write it this way because 2, 2 belong to watch node. So if you want to just so for example, where will this go? So this goes to U2, V2, U3, V3. So that means that it will go to, so this element will go to here. So this is the thing which it will go here. I'll write it with. So this is the element 1 as such can go into this. So the first one goes to U2, U2. Second one goes to UT row and V2 column, and like this. So this exactly fits into this one. Okay. So whereas here this goes to U2, V2 and U1, V1 for the element 1. Essentially it goes to here. So if I draw this here, so the one shown here in the brown, so this corresponds to the element 2 degrees of freedom. But however, you should be a little bit careful here. So here, so this is U2, V2. So for example, this one here, where will it go? So this particular thing, which corresponds to U2 row and U2 column, right? So U2 row here and U2 column. So this is where it should go. So this goes to here, and so similarly this goes to here, right? So like this, so you have to exactly locate where they will go, right? And so that's why the order is not 1, 2, it is actually 2 and 1. So element 3 goes to U1, V1, U3, V3. So that means that it will go here, this part, right? And here, this part, and this part here, and this part here. So this is how this blow thing here. So that blue thing will go here, right? So this will give you, I'm sure it gives you a complete idea where each one of them should go, and remember that they will add on to the earlier existing values. So they will not replace. For example, the U1, V1 here comes from here, element 3. Well, that's of course that's what it is. For example, 3 here. So the 3 U3 V3 here comes from element 1 as well as element 3. So that means that this portion here is being contributed by both element 1 and element 3. So they had to be superposed. So like this, so we can add all these things and make a stiffness matrix here of 6 by 6. So this is the stiffness matrix of 6 by 6. The degrees of freedom being x displacement, y displacement of node 1, and x displacement, y displacement of node 2, and x and y displacements of node 3. And also remember, so this is also equal to, on this side, the equation, if you write it as an equation, stiffness multiplied by the displacements is equal to the equation, the forces. So you can write it as F1x, F1y, F2x. The interesting thing here that these are all external forces, completely external forces. There are no more internal forces as given by the free body diagram. Here, for example, this multiplication will give you, on right side, it will consist of the internal forces as well as external forces, right? So when you add it here, the interesting part is that the internal forces gets cancelled, leaving only the external forces, right? So that way, so this system of equation is the final assembled equations, which obviously in the next stage we would like to solve, and solve for given the external forces. So we would like to get the nodal displacements. So this is as far as the assembly of the equations are concerned. So what we have done so far is that we started off from element equilibrium equations, and then we found out each of these matrices, and then we assembled it here. So this is the assembly of the elemental equations into global equations by appropriately superposing the degrees of freedom. Okay. So in fact, if you are MATLAB enthusiast, I'm sure this can be programmed, and of course people do that, And it's an interesting thing how you transpose the degrees of freedom from element to the final global system of equations, right? So this is as far as this is concerned. And you can see here in the PPT, you can see here that this is the global system of equations. I would say the stiffness matrix K, and I wrote only the upper half, and the lower part is, as we said, it is symmetric because of Maxwell's reciprocal theorem. Okay, so sometimes you can write, sometimes you don't write, so depending upon your patience. Okay, so this is the set of equations, and which in the next step we would like to solve them. Okay, so now let's go to the next step, wherein we would like to apply the boundary conditions. For example, what we were given there in the original problem is that we have externally applied forces, 100 kilonewtons and 200 kilonewtons at node 1, as well as those were the force boundary conditions, as well as we have the supports at node 2 and 3. Obviously, they will impose a certain kind of restriction on the moment of 3. You can very well see that 2 is completely restrained. It cannot move in x and y displacement. And as well as node 3 is x and y displacement. So there are 4 displacement boundary conditions at node 2 and 3 together, and a set of force boundary conditions on node 1. So the important part here is that what is the necessary boundary conditions so that the set of equations are solvable or solved. So now what we are talking about is that, so this is the basic equation where the whole thing is represented as this is K and this is U and this is F, right? K is equal to U equal to F. That's what we have written on the board, and that's in a nutshell it's represented as K is equal to F. F may be capital. So they are all vectors. K is, in this particular case, K is 6 by 6 and U is 6, a length of 6, and F is a length of 6 elements. Okay, so this is for this problem, but it can be any number of degrees of freedom. It depends upon the degrees of freedom. So in 2D, we have 2 degrees of freedom for each node, and whereas if you go for 3D, so these kind of truss structures have 3 degrees of freedom per node. So that way you can very well imagine that you can generalize it very easily. So now the question is that let's try to understand what is the relationship between the set of equations and the kind of structural mechanics problem which we are talking about here. Okay, so to do that, just to talk about taking a 6 by 6 is a little difficult. So what we do is that let us just concentrate on just one element. Okay, so let's talk about this one element, which we thought that that's the whole structure, and this is exactly the same which we have taken up earlier, and then it's a 2-noded element 1 to 2, and then U1, V1 are the degrees of freedom at node 1, and U2 or Uj, Vj are the degrees of freedom at node 2, and then 1 and 2 is the original configuration, and 1' and 2' is the deformed configuration. So in that process, it gets displaced both in x and y direction at node 1 as well as at node 2. So I hope you are getting the complete picture. So this is the same thing as we have been talking about. And now the interesting part here is that we should completely understand what are the constraints or conditions which we need to put so that this is solvable. So why do we say all these things? So let's look at that. This particular example is the numbers are related to for an angle of alpha is equal to 36.86 degrees. So it's a that has been chosen so that the tan alpha is 0.75. There's nothing great about that. And the matrix equation is a 4x4 stiffness matrix, and U1, V1, U2, V2 are the degrees of freedom, F1x, F1y, F2x, F2y are the applied loads. So if you, as it is, if you look at that, so it looks like given the force vector F1x, F1y, F2x, F2y, right? So what we are doing here is that so this is the system of equation, K times U is equal to F, which is 4x4, 4 components and 4 components here. So what we would like to do is that given force components, 4 force components, so that's what is the external applied forces, and it looks like when we want to solve for U here, the displacement, so it looks like that U, we can solve it using taking inverse of K and multiplying with F. Okay, that seems to be a straightforward solving the set of equations. So, but then there is an interesting fact here. You are assuming that K is invertible. That means that the determinant of K is non-zero, right? K inverse, if you want to invert it, so you have to, it should be a non-singular matrix, and then you are assuming that. But it is not so. Why? It is not so because there are certain relationships in the force components which need to be there, and then there is also a certain, obviously there can be some relationship between the displacements also. So what it is that K is not invertible, and the very related term for invertibility of a matrix is the rank. They are all related. So if the rank of the matrix is less than 4 here, this is a matrix of 4x4. If the rank of the matrix is 4 itself, then it's invertible. But if the rank of the matrix is less than 4, then it is not invertible matrix, and the solution of equations cannot be obtained. So the question is that not only the determinant is 0 and the rank is just not 4, it is less than 4, or it is 3 or 2, or of course it cannot be 0, okay, because it's a, at least there are some non-zero numbers here. So that looks like then, so how do we decide the rank of the matrix? So that comes from the fact here that, as the PPT displayed here, so that 4x4 matrix is coming from structures, right? So any static structure which is under equilibrium has to satisfy 3 equilibrium conditions, right? So that means that the total force in the x direction, okay, should be 0. Total force at all the nodes put together should be equal to 0, as well as the moment of all the forces, external forces, about some point is 0. So this moment is, since it is xy plane, this moment is taken about z axis. So like this, so we have 3 equations. So that means what it says is that the equations here, the components f1x, f1y, f2x, f2y are not completely independent. If this problem is coming from a static structural analysis, so these forces cannot be anything and they have to follow or satisfy these equations, static equilibrium equations. So one such, there can be any set. For example, the following force components, you can see here, f1x being 20, f1y being 15, f2x being minus 20, f2y minus 15. So definitely satisfy the equilibrium conditions. The equilibrium conditions, obviously you can see that f1x plus f2x, they add up to 0. f1y plus f2y, they add up to 0, as well as their moments about any point, either point 1 or point 2. So that means that leads to the moment being 0. So to get this solution, so what we have here is that it appears that if you want to get the solution u here is simply k inverse f, and in all practical purposes it is so, but in this structural mechanics problems what happens is that this k turns out to be singular. Why it is, we're just going to analyze just now. So if that means that the determinant of k does not exist, and inverse of k, determinant of k will be 0, and the inverse doesn't exist. And in particular, you can also relate it to the rank. So that means that the rank of k is less than 4 here in this case, and then if you have more degrees of freedom like n, so it is less than n, and it will be less than that depending upon the type of problem you have. So how do we overcome that? So we would like to get a solution. There may be many solutions, but what is that a solution which we can get it, or in for that matter sometimes we may not even have a solution, but here we do have multiple solutions, and if we want to get a particular solution out of that, so what does that mean to us? So what we are going to do here is that, as we say here, in this particular problem, what happens is that the determinant of k is 0, and in fact here the rank, interestingly, turns out to be just 1. So what does that mean? So if you do Gaussian elimination or a reduction method, so you can do this Gaussian reduction in the sense that you can manipulate the rows in whatever manner, and whatever you do on the left side, you also do it on the right side. And algebraically, linear algebraically, you can add, subtract, and so that you can achieve a certain goal, in the sense that the whole row or whole column sometimes can be made 0. For example, here in this case, so you can add the third row and first row here. So the third row can be replaced by, in this case, in this particular case, so you replace the third row R3 in the new form as R3 minus R1. So if that's the case, in this, it's plus, this plus. So what it means that if you replace the third row by adding the first row to the third row, so you can very easily see that the whole row turns out to be 0. Whereas on the right side, so f2x prime will become f2x plus f1x. Interestingly, if you add these two, we have not given any values for this f2x and f1x. So if the complete third row is becoming 0, and the right side also has to become 0 to have a solution. So that means that if this is becoming 0, so you are supposed to have this also to be 0. What we say is that the augmented matrix should also have kind of the same rank. Otherwise, if it is not 0, then the augmented matrix may have a value different from 0, the rank. So similarly here, you can also see that the fourth row also can be replaced by the fourth row also can be replaced by its addition with the second row, in which case the fourth row also turns out to be 0. And on the right side, so the f2 y prime which is written as f2y plus f1y of the previous status, should also turn out to be 0. So then you are left with the first and second rows. So you can further do, interestingly, is that you can go back to the second row and you can replace the second row by doing a little bit of operation like R2 minus. So what essentially this means is that the second row here on the right side also you have the same thing. You can put it yeah. So on the right side also you should do the same thing. So interestingly, these are very interesting operations here. So that means that the first and third rows are added here. The second and fourth rows are added here. And here, this is a kind of thing wherein if you look at on the right side, so the f1y is replaced by f1y 0.75 f1x. So this is nothing but a kind of physical meanings we can give. So such as this is sum of the forces in the x direction. So if this is 0, this also should turn out to be 0. So similarly, sum of the forces in the y direction. So if this row turns out to be 0, so this also should turn out to be 0. And then what is this one? So this is a kind of manipulation here. So that means that the rows are operated in such a manner that here this is equivalent to a moment about the node 1. Okay. So this also should turn out to be 0. So this is, you can very immediately see that this f1x, f1y, f2x, f2y cannot be any arbitrary values. So they have to have a certain relationship. So these relationships are nothing but sum of the forces in x direction is 0, sum of the forces in y direction is 0, and sum of the moments of all the forces about 0.1 here, but it can be any other point also. So you can immediately see here that the row operations of the matrix, augmented matrix, has a direct meaning from the physics. So these are three equations which will define a certain relationship between the rows. Okay. So in particular here, in this particular example, so if you take f1x is equal to 20, f1y is equal to 15, f2x is minus 20, f2y is minus 15. So it will satisfy these three equations. Okay. So that way, the necessity of this matrix satisfying certain conditions is directly can be related to the physics of the problem. So if you do these operations, so what happens in this particular case is that all the three rows starting from 2, 3, 4 can be made 0 by this operation, leaving here only one equation, only the top equation, for that matter any other equation. Okay. So in fact, we will say that there's only one independent equation and all other three equations are depending on this one. Okay. So we can take the first equation, and if you just look at the first equation, you can say that it's the AE by L. 0.64 also can be taken outside if you want. The inside four components are 1, 0.75, minus 1, minus 0.75, and multiplied with u1, v1, u2, v2 is equal to f1x, which can further be written as u1 is equal to L by AE, right, times 1 by 0.64 into f1x plus v1 into minus 0.75, because the v1 has been taken to the right side, and then plus u2 into 1 plus v2 into 0.75. So this is regarding u1, and then while U1 appears on the left side. So V1, U2, V2 are appearing on the right side. So that means that the solution here depends upon f1x as well as some arbitrarily assigned values of V1, U2, V2. So this whole thing can be expanded to get the whole solution. So it is, in fact, here all the components are written here, U1, V1, U2, V2, and the first equation which is giving U1 is nothing but whatever we have written just now. And then V1, so it just depends upon 0 everywhere except the 1 in the second column. So you can very well see that V1 is simply V1 on the right side. So similarly, you can write U2 and V2, right? So this way, this is a complete solution. This has a very interesting property that if you call this as, so this is the complete solution. So I'm writing it, just writing it as so instead of writing all those values, so here this is the total solution. So the first vector has been written as D naught, and this is a D1 which is nothing but minus 0.7510 and being multiplied by V1, and this is the D2 is nothing but 1010, and this is D3 nothing but 0.75001. Okay, the interesting property here is that this D0 depends upon the kind of force which you are applying, that applying F1x. So this is called a particular solution. Okay, so this is given F1, so this is completely known. Here, this D1 has a very interesting property, is that this D1, D2, D3 have the interesting property that K, if you have K and multiplied by D1, if you look at that, so it will turn out to be 0, right? So whatever K you had here, so in the previous one K is there, so you take that K and then multiply this D1 with 0. So similarly, K times D2 is also 0. And K times. So what does this mean? So what does this D1, D2, D3? So this is a displacement configuration for which, if you having this configuration D1, so the force which is applied, the right side represents the force that need to be applied to get a D1. So what does that mean? So without applying any force, you can have a displacement, right? So this doesn't require any force. So that means that the body is undergoing a certain configuration without the application of any force. So similarly D2 also, similarly D3 also. So what does that mean? So what it means is that to have the configuration of D1, you do not require any force, or you can also extend it further, saying that the body does not have any elastic deformation. It doesn't have any stresses inside, so there is no elastic deformation. It is moving, but it doesn't have any elastic deformation relatively between the points of the body. So that means that it is moving like a rigid body. So that way, this D1 and D2 and D3 are known as rigid body modes. So to have this D1, D2, D3, we do not require any elastic deformation, or we do not require any force application. So the force application is there only in this D0. As you can see, so that F1 is this one. So what does that mean? So do we require this D1, D2, D3 at all? So D1, D2, D3 can be applied without causing any elastic deformation. So these things are applied so that we will have a satisfaction of displacement constraints. So that way, what we say here is that this has three rigid body configurations, this particular element or particular body, and three static equilibrium equations. So this is the interesting part. The number of static equilibrium equations and the number of rigid body modes are equal to each other. Well, in the mathematical sense, you can say that the row rank is the same as column rank. So that is the interesting part. So this is the elastic deformation, and these are the rigid body deformations. So but however, whatever be the value of V1, U2, V2, if you apply here, so it doesn't matter, and it doesn't cause any elastic deformation, it doesn't cause any stresses. Okay, so the important for you, so to completely solve the body for elastic deformations, so you have to arbitrarily put these things. Another very important thing is that, so these D1, D2, D3 are rigid body deformations, or for that matter, any combination of this is also a rigid body mode. Okay, so that means that you can devise another three vectors here which also have rigid body modes. Okay, so what essentially this means is that to get a solution here, you have to arbitrarily give V1, U2 or V2, or for that matter, any other configurations, three configurations, which will fix the rigid body. So that means that you have to apply the displacement configuration. Okay, so that way, so we have the total solution here. So these are rigid body modes, or these are homogeneous solutions, and this is a particular solution. So these are not, again, these are not unique. So you can have other kind of vectors here which also give you the rigid body modes. So similarly, this also can be slightly different depending upon what kind of things are. But however, totally it is a solution. So by giving appropriate values for this, so that you satisfy the displacement boundary conditions. So it is, finally, what we can say here is that we have to apply at least three displacement constraints here, so that you can get a solution. Okay, why I call it a solution? That's because these can be changed as per your requirements to get the same amount of elastic deformations, or for that matter, the stresses and strains in the body, which will have the same value. So like this, so we have what again is that, so these are minimum requirements. So that means that in this particular case, so we have three displacements need to be given so that the rigid body deformations are constrained. So in fact, this is not always the same for all kinds of bodies. So it's not always same three. So 3 is the rigid body degrees of freedom for a two-dimensional body, right? If it's a three-dimensional body, so you have how many degrees of freedom? 6 degrees of freedom. Or if you have another type of thing like a beam. So if you have a beam, then you have different kinds of rigid body modes. I think that also we are going to see just now. So let's complete this, what we have done, particularly this two-dimensional truss problem, which we have shown earlier. For example, this is the problem. We have taken a three-member truss with loads 100 and 200 kilonewtons applied at the node 1, and the configuration is something like 45-degree configuration. And then we have, if you recall, so we went element by element, right, and nodes, areas and all that. So we got this K1, K2 and then K3, and then we assembled this one, and then we got, so this is the point where we are discussing about the solvability of this equation. So finally what we need to do is that for this particular problem, the boundary conditions are at node 2, the both x and y displacements are 0. At node 3, both x and y displacements are 0. So that means u2, v2 are 0, u3, v3 are 0. And essentially you have to find out u1, v1. So now this total structure is 6 by 6 degrees of freedom. Yeah, so this is a 6 by 6 difference matrix. And then F is F1x and F1y are as given the numerical values, and F2x, F2y is 0, and F3x, F3y are also again 0. So essentially you have in this one, so out of this 6 by 6, you have the vector u, 4 values are given to be 0, and 2 force components are 0. What about other force components at node 2 and 3, like F2x, F2y, F3x, F3y, or we call them as reactions. So that will come out as a solution, in the sense that for the application of the load, what are the reactions by the supports. So that can be calculated if needed. Otherwise, we can find out the deformations. So what we have here is this one. So out of that 6 by 6, so we can extract just the 2 degrees of freedom, u1, v1. So the first, in fact, here it so happens that the node 1 here, that is the first 2 by 2 multiplying u1, v1 is given to be f1x and f1y as given here, right? All the other u2, v2, u3, v3 are going to be 0. So in fact, this is a very simple problem. But if you have a large system, so where some deformations are given, and so that means that there has to be a very systematic procedure how you extract this small submatrix which will contain the unknown displacements and applied forces. So this is how we extract. So once you have this one, so this is, you can also observe here, this is a stiffness matrix 2 by 2 and with u1, v1 and f1x, f1y. So this is no more singular matrix. This is a non-singular matrix with the determinant being non-zero. So this can be easily inverted and we can get the solution u1, v1. We can find out this u1, v1 as minus 5 in 10 power minus 4. So that means this is minus 0.5 mm and minus 0.163 mm for u1, v1. So this is how we solve. Another thing you also observe here, that the minimum number of displacement boundary conditions are 3. Okay, and then you can also apply more, but not less than 3. Another very important thing here is that which is necessary, I should explain here, is that if you take one, 2, 3. So this is the structure which we are talking about. So what we have done here, that we constrain both u2, v2 0 and u3, v3 0 and u1, v1 we have applied the forces here. So what we are saying here is that we have to constrain or apply the displacement boundary conditions in such a manner that the rigid body modes of this structure is removed. For example, saying that the displacement of 1 and 2 and 3, like this one, u1, u2, u3, if we define them as 0, so will it constitute the necessary boundary conditions by which you can solve? So if you look at this u1, u2, u3 are the displacements in the x direction. So that means that the node 1 and node 2 and node 3 are constrained not to move in the x direction. 1 is not. So that means that they are allowed. v1 is non-zero, v2 is non-zero, and v3 can be non-zero. So which means that the structure is allowed to move in the direction y. So is it acceptable? No, it's not acceptable for the simple reason that these displacement constraints are not good enough to constrain the structure in the y direction. Okay, so the structure can move in the y direction, and so these are not enough. So we need to apply at least one boundary condition here in the, so for example, we can put it here like this. So what is this here? So what we have done here, so this is good enough. So what we mean by this one here is that, so the kind of boundary conditions which we have applied here, so for node 2, which is a pin type of connection, hinge type of connection, so where u2 and v2 are 0 for this one, whereas here this can move in the y direction but not in the direction 3. So these are boundary conditions which are enough to remove all the rigid body modes. For example, then this kind of boundary condition here will not let the structure move in x direction, in y direction, whereas this one, but still this cannot restrain the rotation. So but however, this kind of constraint here where the node can move here in the y direction but not in the x direction, so this will not allow you to node 3 to swing around node 2. So that means that the rotation is also constrained. So that way we have to judiciously apply the boundary condition that all the rigid body modes are removed. Okay, so this way we can apply the necessary boundary conditions so that the rigid body modes are removed. So the interesting part here, we said that there is a relationship between the rigid body modes and the number of static equilibrium conditions. So this is a very important part, and so that way we can definitely say what is the rank and what is the number of rigid body modes, the necessary boundary conditions that need to be applied. Thank you.